This lesson looks at inclined planes, or what happens on a ramp. So inclined planes, this is just a fancy word for a ramp. It's our fancy physics word for ramps, inclined plane. The trick with inclined planes is to rotate your axes to point them parallel to the ramp. So in other words, if you've got a ramp like this, normally we're used to seeing something like this, x and y. What we want to do in this case is rotate it along the ramp and perpendicular to the ramp. So you can imagine, flattening the ramp or tilting your head. So you've got your x along the ramp and y perpendicular in and out of the ramp. The reason for this is it will let us have most of our forces point directly along the x-axis or directly along the y-axis. If we don't, as you'll see shortly, it gets a bit complicated. So here's the general situation. If you have a ramp like this, and we'll call this lower angle theta, this upper angle phi, and you've got some object sitting on the ramp. Well, what's going to happen is it's going to experience gravity pulling it down, straight down. It's going to experience a normal force pushing straight out from the ramp. And it's going to experience a frictional force that will point either up the ramp or down the ramp, depending on how it's moving. So the thing here is, if you notice, if we rotate our axes so that the x and y are parallel and perpendicular to the ramp, that means that the frictional force and the normal force are pointed along the ramp or perpendicular. And more importantly, we only have to calculate how the object is moving along the ramp. Because the object doesn't move in or out of the ramp, we know that the y direction, the net force, is 0. So what we need to do, though, typically is break this Fg into components. So if Fg is pointed down like this, we're going to have one component that is parallel to the ramp, or perpendicular to the ramp, and one component that's parallel to the ramp, sorry. And that's a poorly drawn diagram because it doesn't look like it matches what we have. So let me redraw that. So if Fg comes straight down like this, then the parallel component is more or less like that, and the perpendicular component is like that. That looks better. So Fg, and then we'll call this like Fg, say x, because it's kind of our x direction, and we'll call this Fgy because it's kind of in our y direction. Now, what angles show up in this diagram? Well, if we look at this triangle that I've got right here, this angle right here is phi, okay? Because this Fg comes down parallel. That means that this angle right here is our phi. And this angle becomes theta, because theta plus phi should equal 90. And so in other words, they both add up to 90. And this right here is a 90-degree angle of what I just drew in. The other way to figure this is, let me see if I remember the quick and easy way. Is it this? No, it is not that. So yeah, this is the way to kind of figure it, is to look at this angle and know that that's 90 minus theta. And that means that this angle down here is phi. So in this case, when you're given the lower angle, we know that fgx equals, that would be sine of theta times fg, which is also equal to cosine of phi times fg. fgy is the opposite, so cosine of theta fg, which is sine of phi times fg. Then, in general, the sum of the forces in the y direction will be equal to 0, which will be equal to Fn plus Fgy. And the sum of the forces in the x direction will be different depending on the problem. But almost always, the normal force pointing out of the ramp will be equal to the gravitational component of the Fg. That's most common, but if there's some other force that's causing a component into the ramp, as we'll see in our second example, that gets thrown off a little bit. But this is kind of the setup, this is the general situation, and then you want to track the motion parallel and perpendicular to the ramp. And that will be like that, and then perpendicular to the ramp will be like that. So let's take a look at an example problem here. What does the coefficient of static friction need to be to just barely hold a block on a ramp of angle 30 degrees? So let's sketch a ramp here, an inclined plane. We've got a block, and we know that we've got Fg pulling it down. We've got the force of friction kind of holding it to keep it from sliding down, and then we've got the normal force pointing out of the ramp. So I'll draw my free body diagram. We've got F friction, we've got Fg, and then we've got Fn. Now, what we want here is we want the sum of the forces in the y direction to equal 0 and the sum of the forces in the x direction to equal 0, because we want no motion. And so, in other words, in both directions, the sum has to equal 0. So if we break this down, Fg has two components, and we know, again, from what I'd said earlier, if you call this phi, then the piece that goes parallel, you got a 90, so that means this degree right here is theta. So we'll call this Fg cosine theta equals Fgy. Then we'll have Fg sine theta equals Fgx. So what we need is that the force of friction needs to be equal in magnitude to Fgx in order for them to cancel out. Likewise, the force normal has to be equal in magnitude to Fgy in order for them to cancel out. So this equation becomes Fn times mu s, because it's static, equals Fgx, which is Fg sine theta. And this becomes Fn equals Fg cosine theta. So now we can do some plugging in. And what you'll notice here is there's a huge benefit to not plugging in values, because a bunch of stuff's going to cancel here. We want to solve for mu static, so that's going to equal FG sine theta divided by Fn. We know Fn is Fg cosine theta, so we get Fg sine theta divided by Fg cosine theta. Fg's cancel, so we get tangent of theta. So mu static equals tangent of 30 degrees, which I don't know what that is offhand, but you can go and plug that in and figure that out. The next video will show a slightly more involved example if you want to check that out.